Welcome, this is Bill Foote, and we'll do a little outside recording today. Might have to say hi to the neighbors every now and then, but this is topic 3, and we're doing relationships, statistical relationships, and here you see one, some side-by-side comparisons. We're going to go through a workflow today. It's a Bayesian workflow. We will do a frequentist workflow in a separate video leading up to, with the same data, with the same questions, uh, at another taping of this. Yes, we still tape these. No. Let's get started here and see if I can find the cursor. Okay. Set the display a little bit lighter there. Uh, Here's where we begin. We begin from the end. We have, in this case, two different uh, coefficients. We'll have to explain in a couple of minutes. And we're looking at them side by side. And we're looking at their range. Each of these in the Bayesian analysis, of course, is a random variable. And we're generating the random variables through a Monte Carlo simulation in this case, all due to the work of Stanislaus Ulam, who fortuitously for us was bored playing solitaire while convalescing from surgery in the late 40s. Fascinating stuff. But here we have some distributions. That's fascinating distribution there. Looks like the double slit experiment from quantum physics. But we're not doing quantum physics. We're looking at oil prices and the impact of a major change in global events, namely a war, on those prices. So we're still on top of that. And we have a new measure down here called KL difference. This is the Kullback uh, Leibler. Let's see if we can pull up all of it. KL stands for Kullback Leibler divergence, which measures how badly can we probably be misled using a model to explain data, for example. Uh, and then there are different levels per data point. We're going to actually compute. This is actually a variant of a law of a odds ratio. Here's the odds ratio over here. Uh, C1 is 2.34 times as likely uh, as C0 in terms of explanation of C0 explaining C1. Now, 0 here in our analysis has always been peace. 1 is the war regime. So we're going to go through all of this. It also does some calculations, other calculations that we need to look at, and confidence intervals. Uh, this is a pretty tight one. Oh, they want to come out. Nope, nope, can't come out. So this is the present. Now what I want to show you here is the spreadsheet engineering approach, which basically assigns a different task to a different worksheet. Each of these tabs are a worksheet. The set of tabs is a workbook. And the first one online here is something I'm going to call design, which is something we've been following throughout the course, where we pose, form, sample, count, and finally infer. And in a sense, this is the feature engineering. You could prompt AIs with this sort of thing. You could certainly prompt your systems engineers and developers with this sort of approach. It follows a very strong structure based upon how we learn and how we infer in order to learn. And it starts with a question: what is the impact of war on energy prices? we make up a model. One possible model was an elasticity model. I've given up on that, by the way, so I'm going to change that. I'm just going to change it to just a price volume model. I haven't given up on it. I think we want to do that in a separate session, mainly because elasticity, sensitivity, measuring the sensitivity itself as a percentage change between, let's say, -2 and +2, with 0 being nothing, and 1 being a 1 for 1, or a -1, a -1 for a 1 change in return structure and so on. That all of that gobbledygook needs to be explained. I think in a separate volume of this book that we're creating. So we're just going to do a price volume model here, where peace is 0, war is 1. That's a binary variable, a Bernoulli variable in our context. And we'll have a constant. We'll have a volume sensitivity. And we're going to add a second explanatory variable, which we'll call lag price 1. So this is all going to be daily data. So that would be the day before. We're saying there's memory in this model to some extent, and we can put these lags back even further. Most analysts do. And they don't use Excel to do that. It's a little bit clunky as it is, but we have divided the sample up into two samples here: a peace sample and a war sample. This, for all of you machine learning folks, this could be the training sample, and this will be the fully operational predictive sample on the right. We could do that. Down here we have a full rendering of how we're going to attempt to understand answers to this question. Bring them forward, discover them. Here's the model, mu. We're saying that y is contingent on v, and p -1, where p is going to be the price. Let's see if I got that right. Yes. Okay. So I've added that, and you can see the two conditioning elements. Now what's left out here is a set of arrows. For example, we could say that P produces that, and those arrows don't like to stay, do they? And the volume produces a relationship. It's also possible that the current level of volume depends on the previous level as well. And we could feed that into this. That's called a mediation. And that would be an important wrinkle in this model, maybe even a time warp in this model, because it's folding time and space, the space of volume, the market space of price, and letting previous prices affect volumes, and then let volumes have a separate explanation, and then let volumes then affect the most likely price, which is what mu is a possibility here. And I think we might want to put a note here, for example, saying that. This is a scratch pad after all. Note to self. Check out relationship between V and P -1. Does yesterday's price affect today's volumes? Oh, I think it does in most markets like this, certainly through contracting. Okay. And let's let's see where that, there we go. Let's put this like this. There we go. Note all the formatting and the documentation. Very important aspects of spreadsheet engineering. So formatting, documentation, separate worksheets for separate tasks. There are three milestone ideas for us to grasp onto when we create spreadsheets. As a fact, we're even labeling, no, it's not a spreadsheet, there we go, spreadsheets. Uh, all of this formation here are priors on the hypothesis. And it forces us, hypothesis formation here in this workflow forces us to think very carefully about what are the right ranges for each of these hypothetical parameters. A constant parameter which says, hey, in spite of everything else, and in spite of anything that might not be systematically happening, systematically, it's A0 or A1. But if we add volume to it, some say condition on volume to correct for any change. Now, I don't use correct, I'm just saying there's an influence there. That's B0. And for the lag price 1, we get another one. Now, I don't know that these are good numbers. I have to check those out yet, and we will look at that. This was set up for the elasticity, going from an elasticity of minus 0.5 through to an elasticity of 1.5, a volatile elasticity. Volume on price of volume here. And the lag price basically introduces memory into the model. Some percentage of the previous price is informative of the current price. Sigma is that attempt to grab at whatever else is out there that might vibrate this whole thing. So yeah, we might have to calibrate some of these. Again, quite a bit of thinking needs to go into this aspect. And that's always been my emphasis, but it always goes back, it's going to go back to the data. It's going to go back and forth to the sample that is indicated or relevant and selected relevant to this model and answering this question. All of this has to cohere. That's the point. It all has to cohere. And this design worksheet will feed the simulate worksheet. Let's look at where that is down the road here. There we go. It has an index date. This is from the data worksheet. And here we're going to be selecting some data from this. All of this is from that worksheet, so it's derived. It's a subsample of the data that we struck over here from Yahoo. And that's all specified in the design, the features engineering, as I've called it. Okay, and we took a data sample here. The exercise here would be to expand on this. And back to the simulate, which is doing a lot of work for us. You can see where we picked up these numbers. I actually entered them over here and then copied them over there. It's kind of interesting when you look at this. As you change these numbers, allow B0, the effective volume on price, to be negative. I mean, my God, that's 1/2 of the volume. That's a very, very big number. And we're going to find that these are going to be pretty small numbers. Okay, the volume in this model ends up being right here. It's called an X. The Y lag 10 here is going to be Look at that. We're using index and match to find it out of this table. Very useful thing. And that's something to look up, index and match. It's basically reading this way: find or report the value in Brent that has exactly the same row as Z2 in Brent, minus 1. That's where you get the lag, minus 1. So it's looking at itself, minus 1. Okay, find that row, and that row here is, let's see, what row is that? Oh, it already changed again. Every time you touch this thing, it changes. An F9 or calculate happens. 67.52. There it is. So we should see a 69.4, and we do. Over here, we see a 69.4. So all of that's working. So that's that sheet. There's other things in this sheet that we will attend to in a couple of minutes. Let's get back to the design. There we go. Jumping around just a tad. So this will probably work, which means this will probably work. I might want to put a minus sign there to make that work a little bit harder to find a negative number there. A downward slope. Okay. We're looking for the range because all of these parameters are random variables in this model. They're not a single point estimate, which is a totally different work process. Okay, so here we have data coming in from the sample. It's going to feed our ideas of this when we do a prior check on using the data. It comes from Yahoo. There's a particular designator. I actually got this data by through an R program that brought up the an API, an application interface with Yahoo. Those things exist. They're in constant use, and they work really well. As long as you got that indicator and it's there, and it will pick it up. I don't have the premium license for that, so it only picks it up one at a time. I think I can get WTI. The difference between Brent and WTI is important in these analysis, mainly because, and I would put that as another variable in here, that gives you what is known as the basis. It's a physical basis. The fact that it takes nearly, sometimes up to 2, maybe 3 weeks, depending upon the Atlantic, to sail a ship full of Brent oil over to, let's say, Bayonne, New Jersey, as an example, or the offshore, actually, and lighter it in into New York Harbor in order to produce number 2 oil and gasoline at Linden, New Jersey's set of refineries for distribution across the Northeast. Also power plants. There's a variable frequency transformer there that regulates power from the west to the east. Amazing stuff going on, lots of technology, and important for this analysis to the extent that energy is, there are many voices in the energy world, and they're all prices and volumes and representing trades and contracts and so on. We have a from to February 10th to March 13th. Ooh, the cats are quarreling. Daily frequency, we're using the close of the day. We could use a more clever one which impounds. Bill Baranek did this with somebody a long time ago, used a nice formula for that. We should pull that up out of JFQA, Journal of Financial and Quantitative Analysis. Collinearity. Oh, definitely check collinearity. We have heteroscedasticity already impounded into the model, so we're not worried about that. We split the model into 2. We have 2 different sigmas. That's the heteroscedasticity. The other movement in, well, kind of like risk. Skedask. A lot of different meanings to that. And again, we go from design to data to simulate. You already saw the data to simulation and the design to the simulation. So we saw all of that. Let's get to the count. Now, this is a model we've been using. It's a PERT beta, very practical beta that comes out of the Delphi RAND Corporation, Delphi tradition of tuning the models with expert opinion, um, and then getting a consensus, a range of consensus, partly to have a conversation, partly to see where the model is affected by a change in perceptions. Now, perceptions are important because it's people making these decisions which result in striking a price and a volume. Okay? Yes, we agree. Um, the birds are very, very active with us today. And this uses a beta distribution, which is a variant of the gamma distribution, which we'll also use. Very basic distributions in the family of distributions. They're used frequently throughout our data analytical universe. It's like the Marvel universe of pantheon of things. We don't use just the normal curve. We don't use just the completely uninformative uniform curve. We use other curves to represent our degree of knowledge, should we have any, relative to our feed from priors through the machine that we are building into the posterior probabilities of, in this case, Brent price or and peace. And then we examine the difference and divergence between those two, and we have some ways of answering that posed question. So we see a posterior here. Well, first, these are the formulas for, it uses mid-moment max. It's the min plus a fraction, beta alpha beta will give us those are just two parameters, will give us a number between 0 and 1, effectively a fraction of the difference between the max and the min. But the alpha and beta are built on this thing called Z, which takes into account the proportion of the difference between max and min from the mode to the min. This is key. This is absolutely key. And because of it, we can get a shape on top of our beta to represent our prior opinion. That's why it's been used. PERT, you can look that up in operations research. It's part of project planning. Word projects in it, evaluations in it, R review. I never remembered what PERT always means, but I've used it for years. And CPM. Posterior distribution here is a gamma alpha beta. And the gamma provides skew and kurtosis shapes to what otherwise is a normal curve. The normal curve is, in a sense, a variant of the gamma. You can go from gamma to normal. It is quite a chore. The gamma curve was invented to interpolate between 2 factorials, like 2 factorial and 3 factorial. What's 2.5 factorial? The gamma function and then the gamma distribution built on that was built to answer that question, and thank goodness it did. You can read all about it by doing Gamma Distribution Wiki, which is an excellent article on the matter. And alphas and betas, the alpha is equivalent to a mu over sigma squared, whole thing squared. And the beta is equivalent, this is the shape, this is the location. You see the dominance here of the mu, and the beta has a dominance in the, that is something in the numerator, sigma squared over mu. All scaled, or nicely scaled. The beta gives you the shape. This will give you a mode. This will give you thickness and skews, and oh my gosh, all sorts of good stuff. We're only going to do 1,000 Monte Carlo runs because we have we want to see our results rather quickly. That's why 5,000 are recommended. And we're going to do 1,000 each of two different things. So, okay, so we got that. There's only going to be what we call one chain. This is Monte Carlo with Markov chains with one chain. Normally we use four chains and mix them, simply average the results. That's very, very typical. Look at Stan Ulam, U-L-A-M, probabilistic programming language. The design, this will feed directly the simulation worksheet. Let's look at that worksheet right now. And we have looked at this before. You can see we have an expanded display panel of things that go bump every time you press function F9 on this laptop. Let's do that. And there are things that are sensitive inside of this, so we had to be a little bit careful. We'll get NUM errors at times and so on. There's all sorts of troubleshooting when you do things numerically. Things don't quite fit. You get negative numbers when the distribution doesn't take a negative number. There's something called analytic continuation that we can solve that with. The mathematicians, thank God you exist, as well as the accountants. They keep us correct and keep us asking questions and help us out, and especially numerical things. Here's our priors and all of the rest of the technology we need to produce that beta PERT. Now notice it's the inverse. And the inverse is something we have known for a very, very long time. This is actually called the inverse probability method, invented a long time ago. Miss Marquis de Laplace knew about it. Monsieur Lagrange knew about it. Herr Dr. Gauss knew about it. De Moivre knew about Abraham de Moivre. All these people who worked all of this, I believe James Harriot and Blaise Pascal knew about it. Okay, it's buried in some of their writings, and that goes back in 1500s, 1600s, 1700s, 1800s, 1900s, and then we lose it in 1925 to a need to calculate things easily on calculators and in a workflow that worked every single time mechanically. That's what a major contribution by Ronald Fisher, who went on from there to expand our knowledge of what is called asymptotic inference, which is very, very important to frequentist analysis, but is not important in this analysis. Okay, they deviate from that. It's an interesting deviation. You can get them to converge if you want, but it doesn't matter from most points of view. Roger Kunker at University of Illinois at Chicago would definitely beg to disagree, and he has one of the Bayes in the Bagnio is one of his very, very good articles. A little bit of Dr. Samuel Johnson's snarkiness there, but very well taken, because all too true, as good satire is. Anyways, back to this. No more English reading courses here. Where each one of these is now, you see that, there we go, beta inverse, beta inverse, beta inverse. And notice that this takes on a 0, and this also does here. I'm going to probably change that to something else just to see what happens. And then over here on the right, similar numbers. Okay. As we go forward, that's how this will pretty much work. Now, these calculations here do a width of an interval that we will use in the post-predict tab in a moment. But we're trying to get to this number. This is the model. This is the actual data. Notice a huge divergence in this particular case. And we might want to calibrate these a little bit better. Make them tighter around maybe minus 0.05, 0 plus 0.05, something of that nature. And that's another task for us. Okay, because we need to see that these things are simulating something close enough to give us some inference on what is the price given the data, given the hypothesis, given peace. Over here, given war. Okay. Here are the volumes. Now the volumes were originally in full amounts. It's 197,523. It's also good to scale our data so that it's roughly similar in scale. But we have to remember that, and we have to detail that, and indeed, I think it is indeed detailed here in the data. No. And I need to add more data here. We got volumes converted to per thousand. There we go. There we go. We probably should have put a D there. Wonderful. On the run here. On the run. Back here. Now, there's a routine in the background that all this is recalculated in the background on this routine. And then the routine takes this range which is called interface. You can see the name of it is interface. And then copies it here, not on top of this, but with an offset of 1. So it'll copy it here. And then it'll then look at this as the last run and not overcopy it. It'll copy it here until we get to the number of runs, which happens to be 10,000. So this is the simulator right here. This is the flight simulator, yes. And having gotten all of this, if you ran A0 draws, you would see that it's a flat curve. It looks an awful lot like a slightly modified uniform distribution, as well as B0, C0, sigma 0. Mu 0 doesn't. It's gonna look quite a bit differently than that. And then we get all these other draws for all of the other things that we want. We have this inside here already, and it's just drawing from this and this, so we can track back any transaction here, any calculation that we want. And sometimes we need to in order to spot trouble, spot errors, fix the errors. The design then goes from there. We did all of that, design to simulate. Now we're in posterior prediction. And that tab is, oh my gosh, it's way down here in post. We're now in the inference part of life, where we're also going to do EDA, exploratory data analysis, a la John Tukey. Let me write his last name out for you. 1967. This guy had some amazing insights about what data is and how to explore it. Just incredible, and we thank him for that. We have here. We're going to be calculating all these things. We're going to be doing 2,000 runs here. Why? Well, I'd like to do 10,000. Okay, if I'm on my laptop in R or Python, that is like here the finger snap. It'll get done almost that fast. With all the overhead of Excel, no, it's not going to get done that fast. Even if I put it into an automator. Now there is an automation in here that we should have maybe a topic 4 discussion about in Excel. Something called LET or Lambda in Google Sheets. So we'll put that on hold for another time. That allows us to do Haskell like the LET does anyways in Excel. Haskell like programming user functions, basically, some of the user functions right in a cell and create arrays and all sorts of things. That is a real helpful thing, but I found it also to be kind of volatile, so we got to be a little bit careful, and I don't know where to be careful yet, so I'm not advising it yet. As we go forward, let me put this in a outside border without, there we go. Yeah, much nicer looking. All of this we're going to use an 89% credibility interval. That is not a confidence interval. That's a credibility interval or a probability interval, PI. We could use that too. Maybe I'm going to write that in there. AKA PI. And it's similar to what is a high density posterior density posterior interval, probability interval. Okay, divergence. We're going to use this idea of Kullback-Leibler, which is just comparing log odds. It's odds, but log odds because you can add and subtract odds. It's very hard to do that, but you can add and subtract log odds very nicely. Okay, that's the beauty of it. That's the simple reason for it for right now. Logs are a scoring mechanism that are additive when things are otherwise multiplicative. Yes, something to ponder. In the presentation sheet that we saw originally, we'll have panels side by side, user choices. So we're going to be needing to generate all of these. And we have a worksheet called control. So let me show that quickly, which has in it the variable names. And these variable names come directly as data from another sheet, and so on and so forth. And this one here is what we set up on our own. We might want to use 95 here to compare it at some point with an ordinary least squares version of what we're doing, which would be an illegal one from most points of view because using lag prices, and unit roots and modified Dickey-Fuller stats and Turbine Watts and statistics will be needed. But we're not going to talk about any of that. We're going to talk about this and let the plane go by onto LaGuardia. Hope things are coming from LaGuardia. Hope things are there. Pray for those pilots and their families. Yes, that happened this weekend. Let's go to the post predict. This is where we're using the predictions. We're using A0, A1, C0, C1, mu0, and YDH0. Okay, so our simulation comes up with this. Here, it all comes up with this. Where does that come from? We go. Okay, so we can use anything here, but we don't want to reset that. We want to have peace and we want to have war versions of the model. So we take the min of this, the max of this. Where is this? Well, if we look at it where it is, it's actually in another sheet. And we got so many names. We can make a dictionary out of this. Not a problem. There we go. There's YDH0. It is what we drew in the original simulation out of this. It's in AT, and it's labeled, this whole range is a variable now, called YDH0. We have one for all of these now. Okay, and that's how this starship works. Yes, indeed. And that's, so we have beginning, end, and midpoints all the way through, and we count all of the instances in which the YDH0 distribution occurred. So we got it. It starts at $30, ends here, ends at 158. That's too high. We got to do some recalibration there, no doubt. But the idea is right. And here's our posterior count of how many times. Here's our relative frequency, which is a probability distribution in our way of looking at it. And here is it's really a CRF, cumulative relative frequency here. Okay, see it all adds up to 1. We do the same for WAR, and you can see it's almost the same distribution, but not quite. They diverge, and we're going to want to see how the shapes of these two diverge. That's what the Kullback-Leibler approach does. So we have that, and then we use that over here to take these otherwise uninformative ranges from here 55 to 68, all right, minus 0.3, and so on, all of these, peace and war, to reshape it in the likeness of G, of this CDF, which comes from what we just found out, came from our original piece. It's the posterior probability, and it will do it the same way for each one of these. Now that's a first order approximation. We want to perturb that a tad so that these distributions don't look exactly the same. They will have the same shape as this, though, no doubt, and their divergences will show that they have roughly the same shapes all the way through. So having done that, we then simulate. This is the complex index match system that we use to match, let's say, YDH1 with all of these and produce all of these. These are all going to be now in the shape of YDH1. Okay, and this is a fairly complex lookup that we can walk through some point. I think this is going to take 20 minutes to walk through, but it works beautifully. And you can tear it apart by doing the match of something. The indirect just looks at this A1. Okay. Looks at this A1, which we have from the prior, and all very nice. Looks it up there and then asks, what is the appropriate price in YDH1 according to YDH1 CF. So this is literally the lookup filter, if you will. And this is a massive filtering. That's really all it is. So we do that 2,000 times. And now, for whatever things we want to look up, like A1 post, I just put these over here in order to play with these a little bit. You get similar distributions. Matter of fact, they're the same because of the same shape, but across different ranges. And that's an important aspect of what we're trying to do, sigma. And we could do some more. I just put those out there for fun. Now, we learned how to do all of those, gosh, back in high school maybe. Now we're actually using them. Yes, very numeric. It's a very different way of thinking about this. This is all post-prediction. Okay, we use all of those to do an analysis now. Now this is the analysis built on top of the post-prediction. We're using C1 here. This is fed, as you can see, it comes from the user. The user chooses this comparison to produce. Okay, and then this sheet computes all of these summary statistics regarding the 2,000 C0 posts, the 2,000 C1 posts, and how they compare. The naive correlation, the correlation where all of these things are equally likely, shows a very high degree of correlation between the two. That's kind of interesting. And KL divergence says the same. Now the KL divergence, uh, this is the number of nats, similar to bits. Nats because we're using the natural logarithm. The number of nats needed to make up the difference from C0 to C1. Or put differently, it's how misled can we be about C1 if we use C0 to explain itself, or to have war explained by peace. Okay, that's pretty strange. Yes, and we have all of the other things, credible intervals. All of this comes, you see, this is a choice that comes directly from the user, and these are the quantile and min max and all sorts of interesting things here that we can use to make these work. That should be a 0 there for that fence. This is the Tukey fence, which we can discuss sometimes. IQR is the interquantile range. We can change our quantiles right here if we want. This is where we'd have to change them, not there. Okay, and all of this analysis is brought forth by this and this plot. This plot. You see a plot design came up here, and if you look at the select data, there's a lot of different plots that can be done, but I've chosen these, and it's still too busy, but live with it for a moment. And all of these are, if I edit one, let's see, okay, you see it's a scatter, X and Y. My favorite plot because it's the one I can manipulate the easiest to get the results I need. Okay, so this is just an XY plot. I don't like the histogram so much. I've seen that the bins don't work very well at times, and I don't have a lot of control over it unless I want to do some programming, which I don't want to do. This. Well, let's look at the model itself. Let's look at YD0. That's the model outcomes. And you see it does have the same shape as C1 post. Now you see that there's the divergence. You see this divergence. The distance between here and here on the probability scale in log odds. Well, this allows us to add odds up. Okay, when you make a logarithm, you can add odds up. Otherwise, you got to do some sort of very interesting cross multiplication, a Cauchy multiplication to get it. We don't want to go down that road. We don't even know what that road looks like. So let's use the logarithms. That's why Napier or Napier for some invented it. Okay, now this is a comparison of the two, and we see anything less than 1 is pretty good because the odds associated with this, when we transform it back, are basically 1 to 1. Okay, they have the same shape, but not the same means. And they also have the same shape in the tails, but not the same lower and upper bounds. So all the Kullback-Leibler divergences do, as well as the F-test in the Frequentis ANOVA, is they talk about overall are the two shaped the same way. More so here than in the F-test, but the F-test can be shown to be a variant with a lot of constraints and restraints of this kind of divergent analysis. Likelihood ratios are basically what are going to be going on there. And again, that was another great contribution by Neyman Pearson. Pearson, who named the Gaussian curve the normal curve to his chagrin, Neyman, and they were all working together with Fisher and others to figure out the information impact inside of all these. Claude Shannon invented pretty much modern information theory built on their shoulders and on John von Neumann's shoulders and others when they were trying to figure out what information is being communicated by protons and neutrons and particles. Or looking all of at all of us decision makers as atoms now, okay, which we're not. The atomistic, economistic approach. Thank you, Michael Pearson, for changing our points of view, and others. Steve Keen and is working very hard in that regard. Uh, Different way of looking at things. Tony Lawson, we're questioning this, okay, because we're not getting coherence. So we're all human beings who work towards coherence. That's wonderful. This is pretty coherent. Same shape, okay? Scaled differently, but basically the same shape. And the shape is the thing up here and down here. In the middle, that they move here doesn't matter so much. You see the distributions are very, very similar, okay? Not in range, but in shape. In shape. Shape. Roughly the same skewness, roughly the same kurtosis. Shape, okay? Very different standard deviations, very different means. Fine. The ranges here are pretty close. But you see, that's too big. We're going to have to do something about that. There's no way a peace price is going to go up as high as a war price. Oh, maybe. That's what the model says, but I don't believe the model. I believe our analysis of the model. Back to the design. Okay, just to see what we have there. We have a divergence. We can change the 89%. Let me change that right now because I want to show one more thing before we drop off here. What if we were to use a 95? There we go. And a 95 for this. And what if we were to look at a post? Peacetime. Okay, that's the constant price. That's the base price that we're talking about. That goes as high as 67. And this one, it works well. We've got a calibration to do with B, I think. And B1 post. Now, what are we looking at here? Oh, not B. Don't want to do that. That's a mess. All right, A1. There we go. Okay, now we're comparing the constant coefficients. If we, this is another pain at times. Let's zoom it in. There we go. A little bit easier to see. Do these have the same shape? Oh yeah, very much. Very, very similar shape. We already knew that from looking at the final draw from gamma functions based upon the entire model of prices, peace and war. So these shapes here are basically the same, just scaled differently. Okay, so the divergence, not so much. And you can see how correlated they are. Now, this means that information is being passed from a peace to a war situation. Why is that not intuitive? It's very intuitive. Same people are pushing the save buttons and the transact buttons and the monitoring buttons and writing the same contracts and so on and so forth. Same actors are out there. So they're doing things pretty much the same way in peace and war. That's an insight out of this that we do not get so much out of any other kind of an analysis. So behaviors seem to be roughly the same, and we get pretty good numbers here. Now notice 57 and 64. Keep that in mind. If we go to the storage unit over here and look at an ANOVA test. This is a standard ANOVA, which we will go through. I'm not going to explain it, but I just wanted this is the war, peace, dummy variable, indicator variable, dichotomous variable, Brent volume. I don't have lag Brent here. Notice this is 67, which is our minimum. The T-stat says this is a really good. Don't reject the null hypothesis that 67 is 0. Reject the hypothesis that 13 is 0. We don't know that these are good numbers. This is that we can reject that hypothesis. And this is the hypothesis on more. Volumes don't matter according to this. I tend to disagree, but okay. So we get a low, 95 low of 60 and 73. Keep that in mind, 60 and 73. Let's see if I can get back here. Nope, we don't want to see any news. Thank you. Heavy snow warnings, lovely. For some reason or other, I can't get over there. Let's push this out. What problem of doing this? It doesn't want to do it. Oh, there we go. Finally did it. Thank you. Aye. We got 57 and 64 here. So we're getting similar, but not the same confidence intervals with the other analysis. Okay. And when we add the dichotomous variable, we should get another 20 and another 30 according to this. Getting another 13. Okay, so it's underestimating it. It's a little bit too tight here, and it goes from a 4 to a 22. Yeah, we have to be. There are divergences, and there are divergences because this analysis does not take into account the shape of the data itself. It takes into account the fact that the assumption that data is equally likely everywhere. And that's the ANOVA trick. We will go into that table. It also says that this relationship is fantastic, which it is. It's pretty good. It's not bad, but I would tend to disagree on that too. So we're nearing our end here. This will be again something that we will go through, be able to show how we can get all of these numbers from a calculation on this using formulas we already know how to use, which are our expectation formulas, where the expectation is a uniform distribution probability. All things are equally likely. So this is not an invalid analysis, Harley. It's very useful analysis, and people use this all the time because it's in Excel. Easy to find, sometimes easy to use. You go to data. If we can go to data, and it's in data analysis. It's under regression. And you just fill in each of the ranges and whatever you want to use here. I use 97, but you can use 95. That's what Ronald wants you to use. As an example, by the way, and everybody thinks he wanted you to use it. No. The 1 in 20 rule for errors. And then you can plot it with residuals and so on and so forth. Something called the normal probability plot. We wouldn't use a normal probability plot. We would use a gamma probability plot. And that might be something for the future. Oh, it contains non-numeric data. God help us. Cancel. There we go. There we go. Excellent. This is an ANOVA table. We can come up with a very similar table, but I don't know how instructive it is using the divergence measure. Our divergence measure would be the f-stat. This looks at variations between the model and what the model doesn't do, the so-called residual or unsystematic error. And it uses a notion called degrees of freedom, uh, which is very familiar to us in terms of how uh, certain calculations like variance and standard deviation depend upon a previous calculation. And in this case, there are two calculations, a Moore calculation and a volume calculation, to get you an idea of the model calculation for Brent. And that's why it's two degrees of freedom there. 21 plus 2 is 23. We have only 23 variables here. Is that possible? No, we have 24. Interesting. Get similar stats. If we just make these a little bit easier to read. Simple formatting will do that. Just numbers. There we go. A lot easier to read. And something called the p-value, which some people say is a probability value. You can interpret it that way, perhaps, with a lot of caveats. Basically, it's a score that tells you whether or not an hypothesis about 6713 or 0.05 is different from some other number like 0. And here a p-value indicates yes, it's different. Yes, it's different. No, it probably isn't, because the p-value is going to be using a 2.5, 0.25 score to mark that out. How that comes about is a whole technology associated with the frequentist analysis. We can do a similar one with Peace and Moore down here, which you can look through this entire piece. It's down here in the storage unit area for now, and a little bit more detail on that in a future video on this one. So we just did A1, A0, and so on, and we can do other comparisons too. We can do B0, the sensitivity one, which is a bother to me right now. I think we got it misspecified. And that goes in these ranges, and as you can see, it doesn't even look up here. And this is, again, go down to format axis, do a reset, and now you can see it. Now, are they the same shape? Yes, again, they're all the same shape. They're the same shape because, remember, it's using the model simulation shapes for price given data and hypothesis for Peace and Moore. And as we already saw, they're very similar shapes. And everything else is shaped off of that to a first order, again, in order to get our resamples of the posterior simulations. Now you can get a similar approach by what is called bootstrapping, and that's another topic for another time, more advanced topic. We're doing enough bootstrapping as it is here. As you see, I came in, it was got a little too busy outside with LaGuardia Airport flying overhead. We're in their flight path today. Apologize for any disturbance that might have caused. So we've done a walkthrough of just about everything. The only thing I don't think I looked at was this. We still have some work to do here. I'm trying to build a scatter plot. So again, professionalize your practices with spreadsheets. You'll be able to reuse them. it'll make you think about what you're doing, which is even more important, and it gives you a memory of what you did. For example, this is the memory using something called formula text of a cell of what I did. I can remember what I did here a little bit more easily, and I'm going to need that more, I think, as I go on. Down here are max and lower and upper bounds, something called an AB line, and we may have a separate video on installing those inside this diagram. Right now I'm not so worried about that. We already have them over here very nicely, but it would take this data and make a vertical line and another vertical line. And then we would have it in our legend. So we'd have a more complete, busier situation here. I also overlaid these. That need not happen. For example, I could do this. Those are the two. One, okay. And that's all you get. Maybe that's all you want. Okay. I like a little richer picture with a little bit more texture to it, but you know, to each their own. And whatever the consumer of your analysis is easier for them to look at. Notice they cross, but they overlap. Okay. What the divergence does actually, just one last thing to look at in the post predict, divergence is calculated way over here, isn't it? No, it's not. Oh no, it's in the analyze. Whew, excuse me. Should be in the analyze. No, notice the analyze is like uh, once you specify what you want to analyze, it does the same kind of analysis all over again. Okay, the form of the analysis is here, 100%. The form, the shape of it. You populate it by specifying a particular series, another particular series. You could add a third one here if you want, or a fourth one, or a fifth one. Yeah, you do all of that. And then here's the same thing all the time. Doesn't change. I have a continuation here because I told you I had problems at times with negative numbers and distributions and so on. There's my x-axis, y-axis. I'm beginning to build a scatter just for the data. But here's the calculation for the Kullback-Leibler. Look at how easy it is. Okay. You take all we're doing is we're taking the two and overlaying them. These are just labels. And 1, 2, 3, 4. They each have each distribution of B0 post and B1 post has 20 entries in it, 20 points on the probability distribution. So it's just pulling those 20 points in here, these 20 points over here. In the calculations, thou shalt not have any zeros here, especially. So we have this little thing here to make sure it does it properly. You can also add it here in the same ways, bunches of ways of doing it. Anyways, we're taking the odds ratio. You see the odds ratio drops from a high to a low. High odds to a low odds. Fascinating situation. We take the logarithm of it so that we can literally weight these and add them up. You can't weight these and add them up. They won't add. It's like a geometric series. You've got to do a multiplicative, raise it to a power sort of thing to get an answer. That it's not even that. It's a little bit more difficult than that. And that's why again, John Napier made these logarithms. So here's the scoring mechanism. Some of them are positive, some of them are negative, because some odds are lower than 1. Okay, they're in favor of this versus this. And all of that's taken into account as pluses and minuses, but we're actually looking here for a weighted average of these, weighted by this probability right here. Is that right? AI, right. Because this is the one that we're worried about. Does this predict this, basically? Does this lead up to this? And is there a divergence? Yeah, the divergences. Nope, no divergence there. It's the other direction, other direction, other direction. And they all add up to a weighted average divergence. And this is not a bad divergence. Now, we're going to have to get into Kullback-Leibler, and we will do that relative to the F-test in ANOVA in another rendering here. But basically, anything greater than 1 is going to be a lot of divergence, a lot of odds, a lot of movement needed to go from B0 to B1 to say that they're close to each other. Okay, that's what that means. Here, you're going to find that this is not so bad. It's closer to equivalent, most likely, because that's what a weighted average probability is, where the weights are probabilities. An expected value, yes, expected log odds. You convert that per data point. You convert that to odds ratios. You see it's close to 1 to 1. Okay, flip the coin. Okay, which means they're pretty close. Right. We want a divergence of 0 or near 0 to say that. Okay, but this divergence looks like it could be negative, can it? Yeah, it would be if we just flip this. All right, so let's leave it at that. Go back to the present. Want to put my curves back in before I forget, because I'm going to save this. There we go. RF standing for relative frequency. Say OK. Beautiful. Save. Control S. I got 95s in there. That's pretty good. Okay, I'm going to leave you with this. Pretty long session, but I hope it was useful for building a design, the features engineering side of it, and then the systems engineering underneath it. Okay, all the rest of it is that. And, separate your software development in that way, because we're building software basically, aren't we? And we're infusing it with patterns and approaches and frameworks and principles being applied to data to infer so that we might learn. I'll leave you with that, and thank you very much for your kind attention, and be sure you continue to encourage one another. Courage, mes amis. Take care, and thanks.